Biophysical methods. UV visible spectrophotometry, ultraviolet visible spectrophotometry, UV VAS spectrophotometry. The spectrophotometry is a technique that uses the absorbance of light by using a substances in a solution at a specific wavelength to determine the substance's concentration. The ultraviolet visible spectrophotometry utilizes the light in the UV and visible spectrum. The light of this spectrum can excite the electrons in the atomic or molecular ground state to a higher energy level, giving rise to absorbance at that wavelength. When a beam of a polarized light is passed through a solution, some of the light is absorbed and the remainder is refracted through the solution. The ratio of the light entering the solution through the solution is termed as a transmittance T, and the absorbance A of a light is calculated as negative logarithm of transmittance. A is equal to minus log into capital T. The transmittance of the light through a solution is calculated following the Lambert's-Beer law, which states that the fraction of incident light absorbed by a solution is related to the path length of the absorbing solution layer and the concentration of the absorbing biomolecules. Therefore, T is equal to I naught by I is equal to epsilon into Cl, where I naught is the intensity of the incident light, I is the intensity of the transmitted light, epsilon is the molecule extinction coefficient, and C is the concentration of the absorbing molecules, and I is the path length of the sample. The Lambert's-Beer law assumes that the incident light is parallel and chromatic, that is, having a single wavelength of light, a wavelength of log I naught by I is termed as a absorbance A. The molecular extension coefficient varies from solution to solution for each different biomolecules. To the principle to be followed, some conditions are expected to exist. 1. A source of appropriate radiation. 2. The absorbing medium must not be turbid and should not scatter any light passes through. 3. Equal path length for known concentration and unknown concentration of sample being analyzed. 4. The incident light should be monochromatic. Instrumentations of a typical UV visible spectrophotometer light source. Usually the tungsten lamp is used for the visible spectrum, while a hydrogen or deuterium lamp is used as a source of a UV light. Monochromator. This produces the monochromatic light having a single wavelength that can be modified to change the wavelength across a wide range. Usually a prism is used to scatter the generated light to produce a monochromatic light. Cuvettes. These are optically transparent vessels in which analyte are placed in the path of monochromatic light. The cuvette can be made of glass and plastic that absorb strongly below 310 nanometer, while the cuvettes made of quartz or silica that are transparent above 180 nanometer. Detector. The most commonly used detector are photo multiplier, the silicon diode, and the diode array. Fluorescence. The fluorescence is the emission of light from the substances that had absorbed light or any other electromagnetic radiations. For most instances, the emitted light has a longer wavelength and have a lower energy than the energy absorbed. This event is known as a Stokes shift. However, when the absorbed electromagnetic radiation is intense, it is possible for one electron to absorb two photons. This two-photon absorption can lead to emission of radiation having a shorter wavelength than the absorbed radiation. The fluorescence occurs when an orbital electron of molecules, atoms, or nanostructure relax to its ground state by emitting a photon from an excited single state. Fluorochrome. The fluorochrome or fluorimeter is a device that measures the intensity and the wavelength distribution of fluorescence spectrum. These parameters are used to identify the presence and the number of specific molecules in the medium. The modern fluorometer can detect the fluorescent molecules concentration as low as 1 part per trillion. Usually, fluorometers are composed of one. A source of light that typically emits a double beam is used. The first beam is passed through a monochromator before passing through the sample. And 2. The lower beam is passed through a attenuator and adjusted to try and match the fluorescent power given off from the sample. 3. The light from the fluorescence of a sample and the lower attenuated beam or detected by a separate transducer and converted to an electrical signal that is interpreted by a computer system. The method for determining the protein structure. The technologies to determine the tertiary and quaternary structure of a protein is time consuming and has been a major drawback to the data interpretation from genomic data. The two major improvements in recent times have seen increased progression in the field of protein structure analysis. The X-ray crystallograph and the nuclear magnetic resonance spectroscopy (NMR spectroscopy). However, both these processes are extremely time consuming. X-ray crystallography. The basis of X-ray crystallography is the ability of a precisely oriented protein crystals to scatter incident X-ray onto a detector in a perceptible manner. The scattering X-ray can positively or negatively interfere with each other, generating a signal called a reflection. The scattering is dependent upon the number of electrons and mathematical functions called Fourier transformation, and it is used to produce a electron density map of analyzed molecules. The structural determinations is based on amplitude and phase of scattering. However, only the amplitude can be calculated from the intensity of the diffracted pattern. For a long time, the only way in which this phase problem can be addressed and macromolecular structures completely solved was multiple isomerase replacement. That is the use of heavy atoms derivatives of protein crystals. The incorporations of heavy atoms into a protein crystals by soaking alters the diffraction intensity, allowing the phase to be calculated. The process has certain drawbacks. The process of X-ray crystallography is extremely slow and requires laborious preparation steps that are exclusive to each protein. 2. The data acquisition is another major drawback for this procedure, as a synchrotron radiation source are required. 3. The third bottleneck is data processing, that is converting the X-ray diffraction pattern into the structure that can be submitted to the protein structure data. NMR, the nuclear magnetic resonance spectroscopy. The NMR spectroscopy is used to determine the structure of a protein in solution. The basis of NMR is that some atoms, including the natural isotopes of nitrogen, phosphorus, and hydrogen, are intrinsically magnetic and can sandwich between the magnetic spin state in an applied magnetic field. This is achieved by the absorbance of electromagnetic radiations generating magnetic resonance spectra. The magnetic resonance frequency of a molecule is shifted in the context of different chemical groups, as a resonance frequency for different atoms is unique and is also influenced by the surrounding electron density. The nuclear magnetic resonance spectroscopy is generally applicable only to small proteins, that is less than 25 kilodaltons. Although the recent innovations have stretched this limitation to about 100 kilodalton. The NMR spectroscopy is carried out in a solution, and it is therefore suitable for the analysis of protein that are resistant to crystallization. Following sample preparation, the major bottleneck in the nuclear magnetic resonance spectroscopy structure determination or data recording and analysis. The data acquisition is becoming quicker with the improvements in structural designs, particularly the novel probes and higher frequency magnet, leading to higher signal to noise ratio and greater resolution. The circular dichroism or CD spectroscopy. The circular dichroism CD describes the optical density activity of asymmetrical molecules as shown by the differing absorption spectra. A in left circularly polarized light LCPL and right circularly polarized light RCPL. This event occurs when a molecule contains one or more chiral chromophore light absorbing group. Therefore, circular dichorism is equal to delta A alpha is equal to A into lambda. Delta A lambda is equal to A into lambda LCPL minus A into lambda RCPL, where lambda is a wavelength of light. The circular dichorism CD spectroscopy is a spectroscopic techniques where the CD of a molecule is measured over the range of wavelength. The CD circular dichroism spectroscopy is widely applied to study the chiral molecules of large biomolecules. Primarily, this approach is used to identify the secondary structure and conformation of macromolecules. The structural, kinetic, and thermodynamic information of a macromolecule can be determined from CD spectroscopy. 1. Many biomolecules are chiral in nature, as 19 of 20 amino acids that forms a protein or chiral along with the quaternary structure of protein, DNA and RNA. 2. The large subset of use of circular dichorism is in biochemistry is in the understanding of a higher order structure of chiral molecules such as protein and DNA. The reason for this is that the CD spectrum of the protein or DNA molecules is not a sum of CD spectrum of the individual residue or bases, but is greatly influenced by the three-dimensional structure of a macro molecules itself. Each structure has a specific circular dichorism signature, and this can be used to identify the structural element and to follow changes in the structure of chiral macromolecules. 3. The most widely studied circular dichorism signature are the various secondary structure elements for proteins such as alpha helix and beta sheet. This is understood to the point that the circular dichorism spectroscopy spectra is for UV below 260 nanometer and can be used to predict the percentage of each secondary structure element in the structure of protein. 4th, a powerful application of a circular dichorism is to compare two macromolecules or the same molecules under the different conditions and determine if they have a similar structure. They can be used simply to ascertain if a newly purified protein is correctly folded, determine if a mutant protein has folded correctly in comparison to the wild type, or for the analysis of biopharmaceutical products to confirm that they are still in a correctly folded active conformations. Electron spin resonance ESR spectroscopy. The unpaired electron possesses a spin ms is equal to plus or minus 1 by 2, and this electron spin is possible to observe in an external magnetic field in experiments very similar to those described for nuclear magnetic resonance spectroscopy. The stable organic compounds usually have a closed electronic shell. Therefore, there are no unpaired electrons with observable electron spin. The electron spin resonance ESR are known as a electron paramagnetic resonance EP or spectroscopy is therefore largely limited to the investigation of reactive intermediates. The metal center in metal ligand complexes often have unpaired electrons and detectable electron spins. The electron spin resonance is therefore mostly used for the investigation of a metal center in proteins or prosthetic groups and to study the metalloenzymes. The common metal centers found in protein are investigated by the electron spin resonance spectroscopy or iron and copper. 1. The energy difference between an electron spin state ms is equal to minus 1 by 2 and ms is equal to 1 by 2 in a randomly strong magnetic field of 1 Tesla is equal to delta delta E is equal to 1.86, that is 10 to 23 joules, corresponding to the frequency of 28 gigahertz, with a 1 pf capacity and a 50 resistant, a decay time of pi approximately 50 ps, corresponding to 200 gigahertz, is observed. 2. The excitation frequency in ESR spectra depends on total magnetic moment. The energy level of a bound unpaired electrons are therefore different from that of free electron, primarily due to the electron orbital angular momentum. 3. The corresponding G factor then differs from that of a free electron. G is equal to 2.0023 and can be expressed as a function of orbital angular moment L and the total angular moment J. G is equal to 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 by 2J into J plus 1. 4. Please note that the orbital angular moment is rather small for main group elements S and P orbital, but can be very large for transition element D orbitals. In the latter cases, the transition energy are strongly affected by the surrounding field of ligands. 5. The ESR is therefore a sensitive probe for the local environment of transition metal and can be used to determine the oxidation state and corresponding to metal center in the protein. An example is oxidation of poisonous compounds by a iron porphyrin protein P450, an enzyme found in the liver. Mass spectrometry. The principles of mass spectrometry separates a characteristics that differ different analyte based on their mass to charge ratio M bar S in an ionized vacuum. The analyte are first ionized in a vacuum and are then introduced into the electric and or magnetic field. Their path through the field or a function of their mass to charge ratio. This their measured property of the ionized species can be used to detect the mass of the analyte with very high precision. The mass spectrometry has been an established analytical technique in organic chemistry for many years. Until recently, however, the very low volatility of a protein made mass photometry useless for the investigation of these molecules. This difficulty has been circumvented by the introduction of technique for effectively dispersing protein and other macromolecules into the gas phase. MALD-MS, mass matrix assisted laser disruption ion mass spectrometry. The such a development version of this approach is the mass assisted laser disruption ion mass spectrometry, the MALD-MS, in which the analytes, usually protein, are placed in a light absorbing matrix with a short pulse of laser light. The protein are ionized and then dissolved from the matrix into the vacuum system. In this technique, the protein ions are generated and then accelerated through an electric field. They travels through the flight tube with the smallest traveling fastest and arriving at the detector first. Thus, the time of flight TOF in the electric field is a measure of mass bar charge ratio. The tiny amount of biomolecules are as small as a few picomoles, p moles to femtomoles, f moles can be analyzed in this manner. The generated pattern is thus termed MALD-TOF. Electrospray ionization mass spectrometry, ESIMS. In electrospray ionization mass spectrometry, ESIMS, the macromolecules in solution are forced directly from the liquid to gas phase. A solution of analyte is passed through a charged needle that is kept at a high electrical potential, dispersing the solution into a fine mist of charged micro droplets. The solvent surrounding the macromolecules rapidly evaporates, and the resulting multiple charge macromolecular ion are thus introduced non-destructively into the gas phase. peptide mass fingerprinting. The mass spectrometry has permitted the development of a peptide mass fingerprinting. This technique for identifying the peptide have greatly enhanced the utility of two-dimensional gels on which two-dimensional ultra forces is performed. One, the sample of interest is extracted and cleaved specifically by chemical or enzymatic means. Two, the mass of the protein fragments are then determined with the use of mass spectrometry. Three, finally the peptide masses or fingerprint are matched against the fingerprint found in the databases of proteins that have been electronically cleaved by a computer stimulated. The same fragmentation technique used for the experimental sample. This technique has provided some outstanding results. For example, 150 yeast proteins analyzed with the use of two dimensional gels. The peptide mass fingerprintings unambiguously identify 80%. The mass spectrometry have provided the name tags for many of the proteins in two-dimensional gels. The molecular analysis using the light scattering. There are many ways to determine the molecular masses or molecular weights of macromolecules such as proteins, biopolymers, and the synthetic polymers. Only one determines absolute molecular weight in solutions rapidly and effectively. The multi-angle statics light scattering MALS and MALS, the multi-angle static light scattering combines the precise measurements of light scattering intensity and concentrations for a rigorous first principle calculations of a solution properly molecular weights, making no assumption of conformation or shape and no perturbation to the sample. The basic principle of this method is and follow. First, when laser light impinges on macromolecules, the oscillating electric field of light induces an oscillating dipole within it. This oscillating dipole will re-radiate light, much like the antenna for a radio station sends out radio waves. To the intensity of the radiation radiate light depends on the magnitude of a dipole induced in the macromolecules. 3. The more the more polarized the macromolecules, the larger the induced dipole, and hence the greater the intensity of the scattered light. Therefore, in order to analyze the scattering from a solutions of such macromolecules, it is necessary to know their polarizability relative to the surrounding medium, that is the solvent. When there are many macromolecules in the solution, each macromolecule scatters light via the induced dipole mechanisms. Hence, the intensity of the scattered light is proportional to the concentration of the macromolecules in solution. Twice as much molecules scattered, twice as much light. Surface plasmon resonance. The surface plasmon resonance SPR is a label-free, non-destructive way to characterize ligand binding, such as an antibody-antigen interaction. The principle is based on an optical effect that can be utilized to measure the binding of molecules in real time without the use of labels. The method is based on the immobilization of the ligand capture molecules on the metal film, usually gold, layered on the top of the glass slide. The ligand is introduced via liquid phase and the changes induced in the surface plasmon resonance are measured as the ligand binds to the capture molecules. Since the technique is non-destructive, the slide containing the ligand capture molecules complex can be removed from the SPR, the surface plasmon resonance instrument, and the ligand can be isolated for analysis by the mass spectrometry. This approach has been useful for confirming the identity of a protein bound to immobilize the antibody. SPR, the surface plasmon resonance instrument, are primarily used to measure the binding kinetics and affinity of molecular interactions. The surface plasmon resonance can be used for measuring the binding between two proteins and protein of an antibody, DNA, and a protein for and many more. 2. The SP, the surface plasmon resonance, is unique because it is one of the few techniques that allows determination of binding kinetics and not just binding affinity as you would get from the tradition technique like ELISA. The binding kinetic or the on and off rates can only be determined with the biosensing techniques that gives the real-time binding data of both the association and dissociation phase of the interactions. The advantages of the surface plasmon resonance are manifold, as it is one, the label free, hence less expensive. 2, applicable on small sample volumes. 3, highly sensitive to large and small molecules. And 4th, the data is generated in real time and it is quantitative in nature. Methodology. The SPR, the surface plasmon resonance instruments are made up of optical measurement system, a fluid handling system, and a sensor chip. 1. The sensor chip is a golden film coated on a glass substrate that has been chemically modified to make it easier and to mobilize one of the binding pattern onto the surface of the sensor. The molecules that is immobilized is known as ligand, and the molecule in solution is known as analyte. 2. The sensor chip is in interface with the liquidic system using a small flow cell so that the analyte can be injected at different concentration in very repeatable manner. 3. The fluidic system provides a continuous stream of buffer following through the flow cell and across the sensor chip, maintaining a very well controlled environment. The analyte is easily injected as a plug into the flowing buffer so that it will interact with the sensor surface for a specific amount of time. 4. The optimal system consists of a light source and detector and varies depending on the exact way in which the instrument is designed. The light source eliminates the gold film, and the detector measures the unique optical spectrum produced by the surface plasmon resonance phenomena. 5. The surface plasmon resonance instrument utilizes a laser that shines through a prism beneath the sensor chip, generating a total internal reflection conditions. Which this occurs. The plasmonic wave is generated on the surface of the gold, where the electrical field of which the wave extended hundreds of nanometer into the space above the surface of the sensor. The reflected light will have a characteristic dip in the intensity at a certain angle due to the plasmonic wave, which is measured with the detector.